Welcome to Brain Vision.
In this question, we are basically looking at how when an atom actually emits a photon, there's always got to be some recoil of the atom or the nuclei because of conservation of momentum. Right at the start, it is not moving. Total momentum is 0. After it emits a photon, right, the photon actually takes away some momentum, right? And the photon has a momentum, therefore the nuclei must move in the opposite direction with the same magnitude of momentum such that they will cancel each other out and will maintain a net momentum of 0. So what we want to find is how much this recoil momentum or recoil energy affects the actual wavelength of photon that is being emitted, right? Because this, by conservation of energy, the energy that is in the recoil plus the photon will be equal to the transition energy, right? Say it is transiting from an excited state down to the ground state. It will emit the photon, right, from say En to E1. I'm gonna call this the transition energy, right? Where, right, just the energy of the transition. So if we were to ignore, right, if we ignore the recoil energy, then the energy of transition will be fully the energy of our photon, right? And this will be equals to hc over lambda, where lambda is the one that is given in the question, right? This is the wavelength of the photon if recoil is not considered. However, now we want to consider the recoil, so definitely the photon wavelength is different, it's slightly different. So how are we going to start from this question? Right, we need to understand that the actual photon energy and actual photon wavelength, right, we're going to label it as this. Therefore, if this is also equals to energy of the transition minus away energy of the recoil. Right, this is the actual amount of energy that is being transferred to the photon. Therefore, the actual wavelength of the photon is hc right. What we want is the the correction delta lambda, which is actually equals to lambda prime minus lambda. So we take lambda prime because we expect this to be a slightly larger wavelength because of a lower energy, right? So we expect this to be positive. So we take lambda prime minus lambda, where lambda is the wavelength, assuming we are ignoring the recoil. So it's just hc over energy of the transition. Now we have to do a bit of multiplication. We take out hc over energy of the transition. I factorize that out, we will get 1 over 1 minus R over E transfer minus 1. Right, if you were just to focus on this part of the equation, this is 1 minus now we can assume that the recoil energy is much lower, much lesser than the total energy of the transition. Right, this is our assumption, and we're gonna revisit to see whether this is actually valid. But the reason behind this is that the nuclei often taking into account the momentum of the photon is often very small compared to the usual momentum of our nuclei because of its large mass. So its motion or its kinetic energy, right, which is p squared over 2m, is actually very small, right, because of the very small momentum of the photon. Therefore, this is an assumption that we always make, and using this assumption, this will be a very small value, and we can use binomial expansion or just Taylor series expansion, right, to expand out this bracket. What we do, we take 1, we plus this term, right, the second part of the term, times the power, right, bringing down the power, this will be just over transfer plus so on and so forth, but we're going to truncate the expansion at the second term, right? So we're going to approximate this to the second term of the binomial expansion. So what we get over here is 1 plus ER over E transition. See that the minus 1 and the plus 1 cancels out. And this is what we're left with. What we can do is we can actually replace, right, the E transfer as hc over lambda over here, and what we should get is ER over hc multiplied by lambda squared. So this is our final expression for the change in the wavelength, right, due to the recoil energy. Now to evaluate the correction for hydrogen atom, right, for an actual hydrogen atom, when the electron goes from n level down to the ground state, right, so just a general n level. So first off, we need to use the conservation of momentum. Right, we know that momentum of the photon is equals to momentum of the nucleus. Energy of the recoil is actually equals to p squared over 2m, where p is the momentum of the nucleus, but it is also equals to momentum of the photon, right? So this is equals to momentum of the photon square by 2m, and we can replace the momentum of the photon with h over lambda. So this would be h square over 2m lambda square. And now we can put this into our previous expression, which is energy of the recoil divided by hc times lambda square. Right, so this is the expression after substituting in our recoil energy. Now to actually simplify this, we should get h over 2mc. And we see that this is actually independent of lambda. Right? This is a very important point because it doesn't matter what wavelength of transition you're looking at, the correction term is always the same. And as such, for any n value, it doesn't matter, it will still be the same correction. So we just have to find this correction, we substitute in Planck's constant divided by 2 times the mass of the hydrogen nuclide, which is just the mass of the proton, times the speed of light, and we get 6.61 times 10 power minus 16 meters. So this doesn't depend on n, and it is very small considering that the wavelength of photons emitted by the hydrogen atom, right, typically around 10 to the power of minus 7 meters, right, for photons emitted. So therefore this correction is really small, and the assumption that we made actually earlier is valid.